Hi viewers, welcome to my class on mechanics of materials. In today's class, I'll once again discuss the topic of thermal stresses in a composite bar, but when they are connected in series. Now let us consider a composite bar made up of two different materials, but in this case they are connected in series. At the end of one bar, another bar is connected and they are constrained. If they are not constrained, if the ends are not fixed, it is going to be a free expansion. This bar can expand in this direction, the other bar can expand in the other direction. So only if it is constrained and the stresses will be induced. But when they were connected parallelly, they were rigidly bonded and without any external constraint. If the materials are joined together, due to temperature change, stresses will be induced in both the materials. But in this case, it should be constrained. The ends should be constrained, then stresses will be induced. So if the material are connected in series like this, if ends are constrained either partially or fully, then stresses will be induced when the temperature changes. So if it is heated, both the materials will be subjected to compressive stress. So it's the same nature of stress will be induced in both the materials, either due to heating or cooling. So heating, both the materials are trying to expand and the constraints will not permit this expansion. So both will be subjected to compressive stresses. If you are cooling, both the materials are trying to reduce in length and it is not permitted. That reduction is not permitted. So tensile stress will be induced in both the materials. Let us assume that it is heated. So materials are trying to expand. Material 1 is trying to expand, a compressive force is acting on it. Material 2 is also trying to expand, compressive force is acting on it. There is no external load acting. So the compressive force acting in 1 and compressive force acting in 2, that must be same. Or if it is cooling, tensile force will be acting on both the materials and those tensile forces must be equal. So the first equation of the composite bar is force induced in 1 is equal to force induced in 2. So the force induced in 1 is, you can write it as sigma 1 A1 and force induced in 2 is sigma 2 A2. So sigma 1 is A2 by A1 into sigma 2. So that way you get a relationship between stresses. So if it is heating, compressive force induced in bar 1 is equal to compressive force induced in bar 2 and sigma 1 A1 is equal to sigma 2 A2 or sigma 1 is equal to A2 by A1 into sigma 2. So stress in material 1 is area ratio times stress in material 2. This equation is similar to the bars when they were connected parallelly. Composite bar, when they were connected in parallelly, you had the same relationship. The forces were equal, but they were of opposite nature. When they were connected parallelly, one was subjected to compressive stress, other was subjected to tensile stress. So in this case, both are subjected to compressive stress due to heating, and forces are equal and stresses are related by area ratio. So sigma 1 is A2 by A1 into sigma 2. That is the first relation. Next, the total decrease in length due to compressive stress is equal to total thermal expansion of the materials. Now both are subjected to compressive stress when it is heated. So the reduction in length due to the compressive stress in both the materials put together, okay, that is equal to the free thermal expansion. If it is free to expand, if you remove that constraints, this bar will expand. That will be free expansion. Okay, free expansion. It will expand, and even this bar will expand. So that is free expansion. But when it is constrained, the forces acting, the compressive forces acting, is reducing that expansion. Okay, reducing expansion of both the materials. And the reduction in expansion is equal to the free expansion of both. The free expansion of both, if you consider, and the reduction in expansion due to the compressive stress induced, both are equal. So summation of the reduction in expansion due to compressive stress is equal to the summation of the free expansion of both the materials. This material, if it's free to expand, it will expand by alpha 1 L1 delta T, and this will expand by alpha 2 L2 delta T due to the temperature change. Now this increase is not permitted, so compressive force is acting on one, decreasing the length, and this increase in 2 is also not permitted, compressive force is acting on it and decreasing. So what is the decrease in length here? Sigma 1 by E1 into L1, a change in length due to compressive stress. Strain is sigma 1 by E1 into L1 will give the change in length due to compressive stress, and material 2 is also changing in length. Okay, sigma 2 by E2 into L2, that is a change in length due to compressive stress. So if you sum up both, change in length due to compressive stress in both the materials, if you sum up both, will give the total free expansion induced in both. You cannot directly say that whatever expansion taking place is reduced. Okay, so you cannot equate sigma 1 by E1 by into L1 is equal to alpha 1 L1 delta T, because the junction also will move, and this junction will move, and it may be like moving in this direction. Okay, it is trying to expand, it can expand in this direction. Okay, and this direction no expansion, but this direction it can expand, so some amount of expansion may be taking place in this, but still compressive stress, it's not a natural expansion, this is not freely expanding, some amount of expansion may be permitted in this, but this will not permit to free expansion. This material 2 will not allow material 1 to freely expand. Okay, it will also exert a force on it. So total free expansion is reduced by the compressive stress induced in both the materials, and the total reduction in length due to the compressive forces induced in both the materials is equal to the total free expansion. That is the second equation of the composite bar. So you got two equations for relating the stresses. Sigma 1 is A2 by A1 into sigma 2. Another relation, sigma 1 by E1 into L1 plus sigma 2 by E2 into L2 is equal to alpha 1 L1 delta T plus alpha 2 L2 delta T. Solving these two equations, you can find out the thermal stresses induced in both the materials, provided you know the material properties and temperature change and the area of cross sections of both the materials. Now if three bars are connected in series, and if they are constrained, again you can form the relation F1 is equal to F2 is equal to F3. The forces induced in all the three are equal, so sigma 1 A1 is equal to sigma 2 A2 is equal to sigma 3 A3. Or taking this, you can write sigma 1 is A2 by A1 into sigma 2, and here you can write sigma 3 in terms of sigma 2. Sigma 3 is equal to A2 by A3 into sigma 2. So you can reduce into one variable, says sigma 2. Another relation is the total contraction due to stresses induced is equal to the total free expansion. So sigma 1 by E1 into L1, reduction in length in material 1 due to the temperature stress, plus sigma 2 by E2 into L2 plus sigma 3 by E3 into L3 is equal to the free expansion of all the three materials. So this is another relation you are getting, and solving this you can replace sigma 1 and sigma 3 in terms of sigma 2. Sigma 1 you are getting in terms of sigma 2, sigma 3 you are getting in terms of sigma 2. So sigma 1 and sigma 3 you can replace in terms of sigma 2. So we'll get one unknown sigma 2, and if you know all the other material properties and dimensions, you can calculate sigma 2. Then once you get sigma 2, you can find out sigma 1 and sigma 3 using this relation. So that's all for today. Thank you for watching.